All right, we're moving on with our work here in our counting unit, and today we'll be looking at factorial and what that means, and we'll do a few examples, and roughly in the middle of these examples I'll throw in an introduction to what factorial it is. But I want to start with a little bit of background first. So a couple sort of warm-up problems here. First example, let's say repeats are okay, and the question is how many 5-letter words can be made, reminding ourselves that we don't need an actual English dictionary word, and we're working with the 26-letter English alphabet. So a reminder of the fundamental counting principle: every decision we make gets a slot. And how many options do we have for each decision? Well, 26 letters, there are no restrictions going on. Okay, and so that's going to be 26 to the 5th power, which is a big number. 11881376. So about almost 12 million. Okay, so 12 million possible different words. But then let's look at this next example. How many 5-letter words can be made that have no repeated letters? So all of the letters are different. And this is my way of sort of gradually introducing you to the idea of factorial, which is why I'm throwing this example in. So we still have to make 5 decisions, so we get 5 different slots. And so let's fill in our words, the letter slots in our words, kind of sequentially. And so let's think about how many possibilities we have for that first letter. There can be 26. But then once I use up a letter, it's no longer available because we want there to be no repeats. Okay? So it doesn't matter what letter I put in. Maybe I put in a Q. That would mean that there are only 25 letters remaining. And then 24, 23, and 22. Okay? So we can do that multiplication, but we're sort of counting down because we're further and further restricting the number of options available once we use some letters in our word. So that's going to be 7893600, so a little less than 8 million. So comparing with what we did earlier, we lost about 4 million possibilities once we added on the restriction of no repeated letters. And then as our last sort of warm-up problem before I really teach you what factorial is, the question asks, when making a 5-letter word from random, what's the probability that all the letters are different? Well, we can just take the 2 numbers that we already have. Remember, probability is a number of ways of getting what you want. So the number of ways of getting all different letters divided by the number of total things that could happen. And in this case, the number of total things that could happen is this 11 million number. Okay, so we can actually do a division here. And we get 0.6644, roughly. I round it a little bit, which is 66.44%. So that's actually an interesting percent. That's almost exactly 2/3. So we have an almost exactly 2/3 chance of getting all different letters in any random assortment of 5 letters. So let's look at the definition of factorial to kind of narrow things down a little bit more and get closer to what we're trying to get to today. So the factorial symbol uses this exclamation point. And exclamation point here doesn't mean excitement. It doesn't mean N. Yeah. No, it just means this particular mathematical definition. N times 1 less than N times 2 less than N all the way down to 3 times 2 times 1. Okay, so for example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, and I think that's 720. Let me check. Yeah, as you do these a lot, you'll get familiar with some of the common ones. Okay? And by the way, just as a rule that mathematicians have made to make things work a little bit better, 0 factorial is equal to 1. So that's just something we've decided is so. And let's keep it that way. Don't think that 0 factorial is 0. Okay? So you want to use factorial when all objects are different, when you care about the order of the objects and when you're using all of the objects. So this last bullet point wasn't being applied up above with our words because we were only using 5 letters out of 26 available, so we wouldn't actually use factorial in that prior example. But really, factorial just means we're counting down and we're multiplying each number as we get to it. So let's do factorial with a couple examples here. And by the way, you want to find the factorial button on your calculator. On mine, let's see if this shows up. It is right above the number 3. So I have to type in the number and then the shift button and then factorial. In a graphing calculator, you often have to go into the math menu and then to the probability menu, and then you might find n factorial or x factorial. But just look around for it. Every scientific calculator should have it. You should never have to multiply manually. Every scientific calculator should have factorial. So let's look at this next one. 4 different poker chips. So I have a red, blue, white, and green set of poker chips. How many different ways can I arrange them in a row? So let's check our caveats up here. So first, are all the objects different? Yep, it says they're different, 4 different ones. Do you care about the order of the objects? Yes, we do, because it's saying arranging them in a row. Okay, so that implies that I care what order they're in. And are we using all of the objects? Yes, it implies, it never says specifically all of them, but it does imply for sure that we're using all 4 objects. So we can just do 4 factorial, okay? And that's going to be 24. So there's going to be 24 ways of arranging those 4 different poker chips in a row. 13 poker chips. How many different ways can I arrange them in a row? So same deal. We already checked it with 4. It's the same problem as before. We just have 13 now. So it's going to be 13 factorial. And that's going to be a much larger number. Let's see if we can figure that out. Is that 6,227,020,800? Okay, so certainly many, many more ways I can do it, and I hope you can imagine that we wouldn't have wanted to type 13 times 12 times 11 times 10 all the way down into our calculator. Okay, but that would, if we were to, it would equal that. All right, it's a good place to stop right there.